Welcome back to geometry for section 23 and our last construction for the section. What we want to do is we want to split a line segment into subintervals. So we're looking for an equal subdivision of a segment. So what I'm saying here is if we have a line segment from A to B, and we want to split it up, in this case, into 3 line segments. So we want to find a point, let's call it Q1 and point Q2, so that each of these pieces are congruent. A to Q1 is the same distance as Q1 to Q2, which is the same distance as Q2 to B. So that's what we want to do. And the construction is a little bit crazy, and then the justification is not quite so simple and straightforward as the ones that we've been looking at. So what I want to do is I want to do the actual construction first, and then go back and describe the process that we did. So let's start with a line that we actually would like to partition, or that we would like to find subintervals of, right? We want to subdivide it. So that's the line that we want to subdivide. And the first thing that we actually want to do is we want to construct another line. So we want to construct some other line. What I'm going to do is I'm going to draw it. It doesn't matter how long it is. A little bit longer might be okay. It depends on how much room you have available, that sort of thing. So it could have drawn it short, could have drawn the angle really small, could have drawn the angle really big. It does not matter. In this case, I'm doing it to conserve a little bit of space. So I need a little bit more space, I know. So let's say, I'm just going to go ahead and move this endpoint over so they match a little bit better. And then I'm going to simply say that, right, AB is the line segment that we want to subdivide. And then I'm adding the line AC. So I go ahead and just add the line AC. Then what I do is, since I want to divide this into 3 subintervals, or subdivide it into 3 intervals, what I'm going to do is I'm going to construct several circles. And the circles should have a radius that I can fit the appropriate number on this new line that I've drawn. So I pick some radius and I draw a circle centered at A, and of particular interest is where it intersects with this line. So when I draw it, I find the intersection point on this line. I call that point P1. Then what I do is I construct a circle with the same radius, right? Call this distance R here. And I construct a circle with the same radius and then mark its intersection over here. Again, that's a distance of R. And then what I do is I call that P2. And then I find one more intersection point from a circle centered at P2 with radius R to give me P3. So all of those segments are of equal length. Now, I want to keep that in mind as I work, but I have 3 equal length subintervals here. Of course, this is not necessarily the total length that I wanted, and I couldn't have simply guessed and tried to do that. That's not going to get me exact, and I want exact. So what I want to do is I want to essentially scale this thing onto the line segment that I want to actually partition. And I do that by constructing a few more lines. Well, actually 1 line in particular and then several angles. So what we do is we construct the line from B through, or actually just to the 3rd point there. Once we construct this line, we call this angle angle 3, and we copy that, right? So angle 3 is at point 3, and we copy that angle over here. When we copy that angle, what we're doing is we're creating a parallel line. So we're just saying we want it here, create a parallel line, bam, over there, create a parallel line here. The constructions that are provided by Khan Academy show you how to construct parallel lines. And in this case, we're just constructing the same angle, so we don't have to have a seventh construction of parallel lines. Okay, so we can, let's see here, construct the same angle measure. We did that in the previous construction. And when we do that, we would find the line passing through P2 that is parallel to the line passing through P3 and B. So that looks about right. Of course, when you actually use your compass and straight edge, it would be exact. So keep that in mind, that all these constructions should be done with a compass and straight edge. All right, so we call that angle 2, right? Angle 2 occurs at P2, and then we want to construct that same, we want to copy that angle one more time to pass through P1. And that looks about right. Of course, that gives us angle 1. And these intersection points are exactly the points that we're interested in, Q1 and Q2. Excellent. So then we would actually end up that these three line segments are congruent. And the justification for that really just amounts to the basic proportionality theorem and the ability to add segments. So the segment addition theorem. And let's see here, in order to use the basic proportionality theorem, they're talking about a triangle in that theorem. So what we want to think of it as is this is our triangle, and compared to what we drew for that theorem, this would be our base, and here we have our 1, 2 parallel lines, or we have a triangle with parallel line. So it takes a little bit of putting everything together, but that's going to give us what we're looking for overall. All right, so we want to describe this process, right? This is how we do the construction, but let's describe this process a little bit more formally. So the first thing that we did is we created the ray from A to C, where C was not on the line AB, right? Not anywhere on the line. So we have a line segment, of course, but we don't want C to be anywhere on that line. And then we constructed a circle at A with some radius, so that way we could fit a number of these on our new ray AC. So, of course, our radius should always be greater than 0, and this gives us the intersection point P1. Once we have that, right, we constructed another circle centered at P1 with radius R that gave us P2. So we construct another circle at P1 with the same radius, and that gives us the intersection point P2. And then finally, we constructed a circle at P2 with radius R to give us P3. Again, that circle gave us the intersection point P3. All right. Then all we had to do was we constructed this particular line, right? This line specifically is the one that we drew without measuring any angles. We just drew the line. So we wanted the line segment from P3 to B. So that was the next thing we drew. Then we copied the angles and we found, right, we constructed angle 2, which we did so for it to be congruent to angle 3. And then we constructed angle 1 so that way it was congruent to, again, angle 3. And that's the previous construction. So that's construction 5. Once we had those, that gave us the intersection points of Q1 and Q2. And once we had that, we have the intervals, we have the segments that are congruent. Excellent. So a nice justification for this, we won't go into all of the details, but we'd like to know why this actually works. So if we do all of this, then what we have is since angle 1 is congruent to angle 2, which is congruent to angle 3, right? They're all congruent. We have a collection of parallel lines, right? Parallel, parallel, parallel. Those three lines are parallel to one another. So we have P1, Q1 is parallel to P2, Q2, which is parallel to P3, B. And that's by, actually that would be by the converse of the corresponding angles theorem. I believe it is. So converse of corresponding angles theorem. Excellent. So once we have that, then what follows is by the basic proportionality theorem and segment addition theorem, we get that AP1, right? So that theorem says that if we have, right, it's an if and only if statement, so we know that these are parallel, and since they're parallel, we get a collection of proportions. So A to P2, right, this segment divided by this segment lengths is equal to this segment divided by this segment. And this segment divided by this segment is equal to this segment divided by this segment. A lot of different ways that we can approach that, and some manipulations give us the following set of equalities. So A1P1 divided by AQ1 is equal to P1 P2 divided by Q1 Q2, which is equal to P2 P3 divided by Q2 to B. But we constructed this, right, each of these segments so that they were all the same length. So AP1 is equal to P1 P2, which is equal to P2 P3, which is that radius that we had chosen. So that gives us that AQ1 is equal to Q1 Q2, which is equal to Q2 to B. And that's exactly what we wanted to get. We wanted to get these equal length segments. So this is the construction. That's what it looks like. Again, make sure that you're using a compass and straight edge. Watch the videos by Khan Academy. Search additional videos. Many of them have, you can see the person's hand. And then, of course, make sure that you're meeting with me, be it in class, outside of class, preferably in my office. Then we can meet and see, right? You can watch me use my hands to create these things instead of a mouse, okay? So we can take a look at these things then. But that's all that we have. That is the end of the section. So that's all that I have for you guys. I'll see you guys again soon in our next section.